Good day to all. Today we are going to discuss the practical questions for class 5. In that class, we have discussed like the introduction to material balance and also with other term like mass balance. And also we have done some examples around the block flow diagrams and also especially one distillation column. And as a homework, I have given to my students like the 3 different assignments. In this assignment, like we have 3 different problems, and the first problem, second, and also as I see the third one is also around the distillation columns. And after you're solving like by yourself these questions, first of all, then you can master your knowledge. My recommendation is to look through all questions first of all, then we'll solve the questions. You can take a picture and also stop the video, and you can do it by yourself and then check your answers with mine. And the second and third question. If you are ready, we can start. So while solving these problems, I will use the help of Excel and also Paint to explain the block flow diagram first of all, and also the streams, and I will show some basic theoretical like knowledge and equations based on these questions. Let's get started. The first question. Let me take a picture. Yes, let's go. So, it states that a liquid mixture is 45% benzene and 55%, most probably, this is toluene by mass, is fed to distillation column. Okay, as a keyword in the first sentence, I need to take like one distillation column. It will be like block flow diagram. And as you know, this is like feed stream that's going into the distillation column, yes? And it said that the liquid mixture is 45% benzene C6 and 55% is C7, okay? This is by mass, by the way, by mass. Weight percentages. Next, the overhead product, overhead with other name, it will be top product, overhead. So we have one inlet and 2 outlet in distillation column. This is overhead, this will be bottom product or top product. So the top product contains 97 mole percentage of benzene, 97 mole percentage C6, right? And the bottom product contains, okay, now we are in the bottom. So it means the remaining one will be toluene, right? 3 more percentage C7. And be attentive here because it's mass, but it's given like mole. It means we need to do some conversions during solving the problem. Next, bottom product contains 7% of benzene fed to the column. Okay, it said that again. Bottom product, the C6 is equal to what? 7% of the benzene fed to the column. So in the feed, we have feed multiplied by 0.45. As you know, this is composition of the benzene in the feed total. And multiplied by, in the question it said 0.07. It means the 7% of the benzene in the feed will be in our bottom product, and the remaining one will be toluene, right? And we'll do some calculations. So we are done with the second sentence as well. The volumetric flow rate, let's denote it like V dash, V dot. This is 1,000 liters per hour with a density 0.87 kilogram per liter. Okay, mass flow rate of the overhead product is required, and mass flow rate and composition. It said that find all of the like mass compositions, mass flow rates, and etc. So let's get started. Let me give you another hints and also like basic assumptions. First of all, as I said, if we are doing some mass balance examples, we need to start with our basic assumption, which is conservation of the mass. In the conservation of the mass, it said that the inlet must be equal to outlet, right? So what's our inlet? The inlet is feed. If I will write briefly, equal to, we have two outlets, right? Overhead and bottom product. I will write T top plus bottom. So this is correct also for the full compositions. If you want to write for example, this is total, we'll use it. Let's write for C6, benzene. In the feed, how much we have the composition of the benzene? It will be 0.45 equal to, what about the top? So in the top, it's like mole percentage. That's why, in order not to like confuse you, I will write just T, and B, it will be B. Instead of B, I will write 0.45 multiplied by F multiplied by 0.07. And the same procedure for toluene, 0.55 multiplied by feed, it's equal to 3 mole percentage C7, but it should be converted into the mass, and plus C7 given in the bottom. Hopefully it's clear. The first our first steps, which are mass balances. Okay, so next we should define like the volumetric flow rate of the feed stream. So in general, if you are not given like the feed stream, you can find it, or you can do assumption. For example, you can take 100 kilogram per hour if it's not given. But in this case, as you said, this is given, like the volumetric flow rate and density. It means I can find easily what is inlet flow rate, inlet mass flow rate. So let's do it. How it's found? As you know, the mass flow rate M is equal to rho V dot. Yes. And I need to do multiplication. It will be, as you see, liter R cancel out. Yes, 870 kilogram per hour. It means that my inlet flow rate, the mass flow rate, will be 870 kilogram per hour. Let's write it on the Excel as well. Sorry. So inlet mass flow rate equal to what? Its value. Okay, this is question 1. Next one. So we can we determine like easily the C6 and C7 as you said? I believe yes, because we are given with the compositions. Let's define it again. Inlet C6, C7 total. As we said, the total is equal to this value, kilogram per hour, and we know that the composition is equal to multiply by multiply by 0.45. Oh, sorry. No, I didn't mistake. Next, and this one multiply by 0.55. This is mass flow rate for all of them. Inlet. Okay. Okay. And let's merge it. It's correct. We have defined like our inlet. Can we find the outlets? We need to define like outlets. So how can we define like, for example, what we are given with the next steps? So for example, we can define like bottom C6. And after determining this one, we can easily find the top product, right? Let's do it. So it says that in the bottom, we have again C6, C7, and total. I don't know right now. Let's write it like its value, as we said, the 7% of the feed of the benzene. It means the benzene in the feed multiplied by 0.07, right? It will be kilogram per hour again. So in the bottom, we have 27, approximately 28 kilogram per hour, right? And as an inlet, we have this value. It means we can also find the top product. So it means that I have determined already, it was 27.405 kilogram per hour. So I knew this value, and I also knew this value by multiplication of this 870 multiplied by 0.45. It will be, let's write it, 391.5, right? So it means that based on this formula, the feed is given, bottom is given, I can easily find the top product, right? How should I do it? Feed minus bottom will give me the top product. So let's see. Let's write the top. Again, C6, C7, and total. Okay, so we know this one's okay, it's equal to feed minus bottom. So kilogram per hour. It means that we have also found, like we have completed our calculations for the benzene in the top, in the bottom as well. Next step. The next step is to work with the mole balances. It is said that in the question, this is given like overhead product contains 97 moles of benzene. It means that this value that we have found by subtracting this feed minus bottom, it will be 3.5 kilogram per hour approximately, right? And this is equal to 97 mole percent, right? So it means we need to find the whole content, like 100 mole percent. So how we will do that? The exact value was 364,095. This is kilogram per hour. This is for 97 mole percentage, but we need to find 100 mole percentage. It said that in the question, again, I'm repeating it. So 97 mole percentage is standing for this mass flow rate. Okay, it means I need to find full total flow rate content in the top product as a top, sorry. So let's find it. How we'll do that? We'll multiply it and divide by 97. Let's do it. So in total, let's write it. Multiply by 100 over 97. It means overall we have 375.36 approximately kilogram per hour. It will be our top product. Again, okay, let's write it. It means overall we have 375.4, let's write, kilogram per hour. It means the remaining one will be C7, right? I need to do subtraction. So it will be equal to minus kilogram per hour. So I have completed already the C6 benzene, and I can also solve for the toluene this example because the feed material is given, the top material is given. I can easily find the bottom by subtracting the feed minus top. Okay, it means this is equal to minus this value. It will be kilogram per hour as well, and the total plus this one. Okay, now let's check. So is our final result correct or not? So how do we check it? So we can first of all solve for the total ones. So the total is 870, right? And the total in the bottom is approximately this value. So let's take it and plus, let's check for the top. Oh, yes, exactly. It means the total values are the same. Their sum has given is given like the 870 kilogram per hour. It's correct. So we have done it correctly. It said in the question that after finding all this mass flow rate, find also the mass compositions. How to do the mass composition? We need to take like the individual component and over the total one, it will be mass compositions. You can also like no, sorry. Let's do it. Okay, and let's write it in the percentages. It's approximately 6 and 94% as a mass composition in the bottom. And let's check it for this one as well. Over the total and equal to over this one. Yes, it is again both mole percent and yes, as you see, it is correct because 100% that we got. Hopefully it's clear, the first question, and that's all. We have already solved this question and determine mass flow rate of the overhead product. We have found it 375.4. The mass flow rate and composition of the bottom product stream, yes, we have also found these values as well. So in the Excel, you can also check your answers. Let's go to the question 2. It will be much more easier to understand the second question. So I am opening the new file. New file, don't save it. Okay, second question. Take this one. Okay, take again the lecture, right? Okay. 450 kmol per hour of N-butanol and isobutanol containing 30 mol percentage N-butanol, normal butanol, is separated by distillation into two fractions. Okay, distillation. So we need to draw the distillation column again. This is feed, this is outlets that we have seen in the first problem, feed, and this is top, this is bottom. Right? In the feed, we have 450 kilomole per hour. As you see, the basis is given with the mole, okay? And it said, in the feed, we have 30 mole percentage N-butanol, 30 mole percentage, and 70 the remaining one, right? So if it's NC4, the remaining is iso-C4, right? The flow rate of N-butanol in the overhead stream, like top, let's write it, N-butanol, C4, this is, it's already given by numerical. And we have also C4 and NC4, iso-C4. And isobutanol in the bottom stream is given, this is 300 kilomole per hour, right? Operation is at steady state. Let's see what's asked. Calculate unknown component flow rates in the output streams in bottom and top. It means what is mole fraction of N-butanol in the bottom stream? We can easily find it. What is the mass fraction? Okay, let's do calculation together. 450 kilomole per hour, it's given. Yes, let's write our first step as material balance. The first one. Second one, for NC4. How should I write it? F multiplied by 0.3, it's equal to what? Top, already given, and plus bottom. When it comes to IC4, iso-C4, it will be again F multiplied by 0.7 equal to top, we don't know, plus bottom is given 300 kilomole. So we can easily find it. Let's do it. So the feed stream is given. Yes, 450. Open the calculator. 450 multiplied by 0.3, it will be 1. Let me keep the color, 135 kilomole per hour, right? And it means that if it's 135, this is 120, and the bottom will be 135 minus 120. It will be 15. In the bottom, it means we got the normal butanol as 15 kilomole per hour. Yes, we have already done like in the bottom stream the benzene balance. Next, we can find the isobutanol. So the remaining one will be our isobutanol in the feed, 315 kilomole per hour. Okay, and we said that 300 is given here. Okay, and the remaining one will be in the top, right? 300 is in the bottom, 315 in the feed, and the remaining one, 15 kilomole per hour in the bottom. So we have done all balance around this distillation column for normal and isobutanol. In the question, it was asked to find unknown flow rates. It's completed. Mole fraction of N-butanol in the bottom stream. So in the bottom stream, how to find the fraction? Overall, this is 315 as you see. Okay, and this is 135. To find the NC4 decomposition, it will be what? 15 individual over total multiplied by 100 percentage. NC4 mole percentage. It will be equal to, 15 over 315 and multiply by 100. 4.76. Let's write it. 4.76%, approximately 5%, and it means the remaining one, approximately 95%, will be isobutanol. And the last question, it was said, what is the mass fraction? So I believe it's asked for the NC4. To determine this one, we need to find the NC4 molecular weight. So we have the kilomole, we need to change it. So NC4, the formula, hopefully it's given here. No, it's not given. NC4 butanol. Let me change it. Where is the screen? It's here. It should be given here, but it will be approximately 74 if I don't mistake, but physical property data B1. Okay, it's 74. Yes, I checked it, it's 74. Let's go back. This is 74 kilogram per kilomole. So in order to the mass conversion from mole to mass, so what was given, like 15 multiplied by 74, it will be my mass, and over the total mass. So in order to do that, I have also converted this isobutanol into the mass, and it will be 15 multiplied by 74 plus 300 multiplied by its molecular weight, and like this is division in the denominator, and by multiplying by 100, it will be my mass composition. So I didn't want to lose time for calculating this one, but the overall procedure will be like this. So hopefully you have no question from this second practical assignment. So let's go the new and the last one. New and the last one. Yes, the third one. In general, I highly recommend actually to work with the Excel, but also the like the hand calculation, to understand the hand calculations. But you can also do, like, first of all, to draw the diagram, to draw the block flow diagram, and then try to solve the problem. Let's go to the paint and our third and last question. Okay, this is again a distillation column. That's why I will directly select this one. Okay. Again, feed, we have overhead and also bottom, right? Top, bottom, and feed. Let's see which components are given. Containing 42 weight percentage. Weight percentage is mass, benzene, and the remaining most probably is toluene. Okay. The flow rate is also given, like 100 kilogram per minute. Great. So products leaving the top of the column, this one overhead, 90%. This is given with the mass, by the way. Very good. The remaining one will be what? C7. And 85. Okay, 85% of the total benzene fed to column exists in this overhead product. Okay, good. It said that 85%, this is equal to 90, it said that in the top product, the 90% C6, it's also equal to 0.85 of total benzene fed to the column. The total benzene fed to the column is what? Feed multiplied by 0.42, right? And it's 85%. This is equal to 90% of the top as a benzene. So our mass bonds will be like this: 0.9 multiplied by T is equal to 0.85, 0.42 multiplied by feed. Okay, and calculate the mass flow rate, mass compositions, and all of this stuff. Okay. Again, the first balance F is equal to T plus P. Let's write it first of all, benzene. This is feed multiplied by composition equal to, in the top we have this equation as you see, 0.85 multiplied by 42 F plus bottom. And as you see, this will be bottom is equal to 0.15 multiplied by 0.42 multiplied by F. So let's calculate it. 0.15 multiplied by 0.42 multiplied by 100. 6.3 kilogram per minute. Okay, good. It means as a C6 and C7, the C6 will be 6.3 kilogram per minute. Okay, and this will be 42 kilogram per minute, and the remaining one will be on the top right. 42 minus 6.3, which is 35.7. It will be 35.7 kilogram per minute. Okay, we have completed the balance for the benzene. Next, I will do it for the toluene. This will be 58 kilogram per minute, right? And we said that we can easily find the top one because the 35.7 that we got from this equation, this is equal to 0.9 multiplied by top, right? If it's equal to 35.7, the top overall will be equal to 35.7 over 0.9, right? Just a second, yes, over 0.9. It's approximately 40. I will write overall 40 is equal to 40 kilogram per minute. So if the overall top product is 40, the remaining will be the bottom 60 kilogram per minute, okay? Okay, and 60 kilogram minute, the bottom total. The 6.3 is the C6, the benzene, and the remaining is toluene, right? It means I need to do 60 minus 6.3. It will be 53.7 kilogram per minute. So I have done my calculations based on both benzene and toluene. And you can also find the remaining C7 from the top, like 40 minus 35.7. Subtraction will be 4.3 kilogram per minute. Or you can find this C7 in the top from the feed 58 minus 53.7. It will be also 4.3. It means we have done our calculations in the correct way. It's like that mass flow rate and mass compositions. I believe the leaving the bottom of the column, we have found the like mass flow rate. If you want to find like the mass composition, it will be 6.3 over 60 and 53.7 over 60. You can find the composition. The volumetric flow rate of the overhead product. So we have also calculated it like, just a second, 40 kilogram per minute. If you want to find like V dot, it will be equal to M dot over rho. So the rhos are given like specific gravities. You multiply by each composition and take the sum of them. You will divide mass flow rate into this rho density of this top product mixture, and you will get like volumetric flow rate. Assuming it exists, yes, that we discussed. That's all actually from these 3 questions. If you have any questions, you can drop the comments in the chat and I can help you, like, I can help you with that, with those questions. So that's all from this topic, and in the next lesson, we'll also discuss additional mass balance problems because you need to do more assignments, more practical assignments to master your knowledge, and then we can go to the like equipment sizing, equipment design, and other process calculations. That's all. See you in the next class.